we're now going to look at two body collisions in one dimension. Let's do that. So what are we going to do here? Momentum is always conserved. So what we've said is that momentum of a system is always conserved if there are no external impulses or no external forces. This implies here that the total momentum before must be the total momentum afterwards. If F external is not equal to 0, then momentum is not conserved. And so what this tells us here is that then I look at the total momentum of the system before, and now I have an external impulse. And what is that external impulse? It changes the total momentum of the system afterwards. So one of the things that I've been saying, and I'm probably going to repeat again and again and again, you're going to see that what we're going to be looking at is conservation of momentum. So when I say the word conservation of momentum, one of two things has to cross your mind. It immediately means that V center of mass is a constant, or P total is a constant. And what does this thing say? It says the following thing: the momentum of individual particles in a system must redistribute. Okay, they must redistribute their momentums after the collision to conserve P total or V center of mass. And one of the things that you're going to see here is that there is an exchange of momentums in the system. That the only way they can do that is that they have to exchange momentums. And that's hard to see, but I'm going to try to help you to see it. And what we're going to look at is that we're going to look at, there are three categories of collisions. The first one that we're going to deal with is elastic. And this is very, very important. The elastic one is probably the most important one. And the reason why, it's an idealized situation. And what you find in elastic collisions is that these kinds of collisions conserve energy, which is not very often. Collisions do not conserve energy for the most part. Then probably the easiest one is completely inelastic. And in this case, what you find is that these guys do not conserve energy. Now, typically, we don't differentiate between completely inelastic and inelastically. But I'm doing this because if you just have a plain inelastic one, again, it does not conserve energy. These completely inelastic and inelastic, they're really the same. But this is the one that you want to watch out for. These are typically the much more complicated collisions. So what we want to do is that we want to go in and we want to get our handle on elastic collisions to see, how we make sense of all of this stuff here. Okay, so there's a lot of equations here. Okay, and what you're going to find here, but there is so much physics here. The physics of collisions is freaking awesome. Man, we could talk, almost everything that we deal with on a daily basis is some form of a collision. Okay, here we go. Elastic collisions. There's a lot going on here. Elastic collisions are perfect collisions. And what that means here is it effectively says that when colliding objects rebound off of each other, they do it without lasting deformation or generation of heat or sound. So that means that the colliding, I'm not really sure what I just said. I liked what I said. The colliding objects rebound without lasting deformation. That means it's able to recuperate all of the energy in the collision, or generation of heat or sound. So a perfect collision is quiet. A perfect collision has no heat, which is
that what happens in a vacuum, or is like an elastic collision possible in a vacuum, or?
Sure.
Huh.
Typically, what we try to do here is that we can approximate them. Yeah, but how do you, if you have a collision, can you imagine a collision without a sound?
Well, I was thinking
So
of a vacuum.
in a vacuum, it would take the sound, but what about the heat? I agree that that vacuum makes it one way of, you can't transfer certain types of heat. But anytime you have a contact, you have to increase the molecular motions in that object. So it's a really, really, the only, elastic collisions that I know of are in elementary particle collisions, like electron-electron collisions and stuff like that. So that's the only ones that I'm aware of. There might be others, but a lot of times people will just approximate it. So if this is the case, okay, then what we find here is that if this is the case, then momentum and energy are both conserved. So when I think about a picture here, you know, a lot of times we'll say like, oh, we'll have an air track. And an air track is a very, very low friction system. And so typically what we have here is that you'll have a track, and what the track has, it has a bunch of little holes. And what they're doing here is that they're actually blowing air up. And as they blow air up, they'll take a cart that lives on this track like this. And what you're seeing here is that if this is one, then this essentially glides with no friction. And then since I'm thinking about a collision, then you could imagine that I have a second cart that's moving in this world. And what I'm seeing here is that these guys are coming in and they're going to collide. So again, this is our before situation. And so if there's nothing else in this world, right? Here's my system. Well, you might say, well, there's the force of gravity. Well, force of gravity is perpendicular to the velocity, so therefore it does no work and therefore can't change the kinetic energies of these guys. So gravity doesn't affect the system. If it's frictionless, then we're saying here that nothing can happen. There's no work by friction that could change the kinetic energy or the speeds of these guys. And since there's no external forces in the system whatsoever, that means I may have a situation is that afterwards, the system can't change. So therefore, if I draw my system again, maybe the system is now going like this afterwards, where I have some final velocity. And then I could have maybe the other cart might be going in the opposite direction, where I'm looking at these guys, and what I'm seeing here is that all I know is that my system did not change. And because my system didn't change, there's nothing external, then that's what we have. So here's what we typically know about a system. So what does one typically know about this kind of system? Well, the answer is we typically know the masses of the carts. And since we started these guys moving, we typically know the initial speeds of these carts. So we know the masses and we know that. So what we can do here is that with these guys, what we can do is that we can then go in and we can predict the final speeds, V1 final and V2 final. Now note, these are vectors. So not only do I have magnitude, I also have direction that I have to account for. So now, here we go. So if I have an elastic collision, must satisfy two conditions. One condition has to be the total momentum of the system, right? Before and afterwards. And what do I mean by the total momentum? Well, that tells me here that I have P1 initial, P2 initial must be P1 final plus P2 final, because that's all in my system. And it must also satisfy the kinetic energy before and the kinetic energy afterwards, because they conserve energy. And since we're assuming no height changes, then that means that this guy has to be what? Well, this has to be kinetic energy 1, 2, and then this afterwards. And so what we find here is that what we've done here is that we have set up a system of 2 equations and 2 unknowns. So let me bring it down here. This
Wait, if there's an external force, will it never be elastic?
exactly.
Okay.
This sets up 2 equations, right? Equation 1 for momentum, equation 2 for kinetic energy, and 2 unknowns. What are my unknowns? V1 final, V2 final. So if you look at this thing, you get this. You get M1, V1 initial, M2, V2 initial, which we know everything about. But on the right side, we don't know the final velocities. And if I look at the kinetic energy, the same thing happens. I know everything on the left, but I know nothing on the right. I mean, of course, besides the masses here, but we're talking about these guys right here. And so when you look at that, you can see that I have V1 final here, and I have V2 final there. And this turns out to be a fairly complicated equation to solve. So this is hard to derive. And so if you solve these guys now, right, we solve for V1F and V2F. This is what you get. You get these complicated looking equations that read V1 final. Then I get masses times the initial plus so you could see that this is dependent upon the masses, which we know, and it's dependent upon V1 initial and V2 initial. And then if I write the V2 final equation, what you'll see here is that look at this second term for V1 final. See how that's 2m2 divided by the sum of the masses? Look at this guy. So it's the opposite mass divided by the sum of the masses. And then look at the diagonal term. This guy has, for V1 final, it has M1 minus M2. This guy has M2 minus M1. And these are an extremely important system of equations. And these are known as the elastic collision equations. By the way, textbooks don't call it that. They just say I don't know what they call them actually. I call them the elastic collision equations. So what I want to do here is I want to do the following thing. I want to simplify this system and then try to get you to intuitively understand these equations. Okay? Because I bet you have a lot of intuition here. So what I'm going to do here is I want to analyze collisions. Let me be careful. I want to analyze a 2-ball elastic system where ball 2 is stationary. That means I'm going to purposely always put this thing to be at rest. Now, the elastic collision equations simplify greatly. Because now you could see here is that V1 final is then going to be that first term. And then, of course, that's going to be 0. So I only have one term. And then V2 final only has this first term too, right? Like this. So this is a real nice simplification. So I only want to use these to do this. So when I start to analyze my things, I'm always going to do two things. Okay? I'm always going to do two things. So I need to ask, two questions all the time. Okay. So the first thing that I got to do here is that ultimately what we want to do here is that we want to do what? We want to find out which ball has, maybe I should do this big. Which ball has what? More momentum after the collision. And it's really going to be, is it the projectile, the ball coming in, or is it the target particle that was at rest? And the way I'll try to answer this is with the second question. I will always draw the momentum bar diagrams to answer all of these questions. I personally believe that the momentum bar diagrams are more important than the energy bar diagrams in analyzing situation.